Welcome back, everybody, to the latest in our Distinguished Alumni Series celebrating our 100th anniversary as a department. Today's speaker is Dr. Kate Grier from the Stewart Observatory at the University of Arizona. Kate got her bachelor's degree at Illinois back in 2007, working with Robert Brunner. After that, she went on to Ohio State to get her PhD, which she got in 2013, and she did postdoc there and at Penn State before heading to University of Arizona in 2019, and she's now an astronomer there. And Kate works on optical and UV observations of AGN, in particular reverberation mapping with Hubble, Sloan Digital Sky Survey, and other instruments. And today she'll tell us about that topic with the Sloan Digital Sky Survey. So please go ahead.
Okay, thanks. Hi, everyone. Thanks for inviting me to come here today. I wish I could have been there in person, but circumstances, as we all know. Yeah, I was a graduate at U of I in 2007. So I dug up a little photo here of our graduating class. There were 6 of us that year, I believe. And when I came in to U of I as a freshman, I didn't know what I wanted to do. I came in undeclared and I wasn't really sure, and I was taking all sorts of different classes. And I ended up taking an astronomy class just for fun. And Professor John Dickel was my professor. And I just loved the class. I thought it was so much fun. And so I was like, well, what if I just keep taking astronomy classes? And so I took a couple more. And by the end of my first year, I was sold. And completely sold. I was like, nope, I'm doing this and I'm going to go to grad school and this is what I'm going to do. So I really had such a great time in the astronomy department while I was there. And, you know, everyone was just great. And I feel like the astronomy department really felt like home when I was there. And so I was really sad that I couldn't get to come back and visit, but maybe I'll just have to convince you guys to invite me again in a couple of years or so once everything's settled down and I can come back. So today I'm going to be talking to you about mostly my main area of research, which is reverberation mapping, but I'll be talking about some other quasar variability related work that we've been doing with SDSS as well. So let me see here. Okay, so I'm just going to start off with a brief discussion of supermassive black holes, quasars, and reverberation mapping. And again, most of this talk is going to be focused on my reverberation mapping work. But at the end, I'll probably spend some time talking about quasar outflows and broad absorption line variability as well. So just a reminder, when we're talking about supermassive black holes, we're referring to those that are hundreds of thousands to billions of solar masses in size. We find these at the center of massive galaxies. Here's just a couple of examples of galaxies hosting supermassive black holes. This is the galaxy hosting the largest black hole ever found, which is several billion solar masses. And here's the famous image of the supermassive black hole at the center of M87. So my business is measuring the masses of these black holes. And so why do we care about what these black hole masses are? There's been a number of correlations that have been observed between the masses of the black holes and various properties of the host galaxies that they live in, such as the ones I show here, which are the luminosity of the bulge and the velocity dispersion of the stars in the bulge of the host. And so the existence of these correlations suggests that there's some sort of connection between the growth of supermassive black holes and the growth of the galaxies that they live in. So to fully understand how galaxies evolve, we also need to understand how black holes evolve. And in order to do that, we need to know what their masses are so that we can put that into our simulations and our theories for how these things happen. So we also need to know what supermassive black hole masses are in order to determine how they form. A big open question is how supermassive black holes form so early on in the galaxy, or sorry, in the history of the universe. And so we need accurate black hole masses across the entire observable universe in order for us to fully explore these questions. So the way that we measure supermassive black hole masses in nearby galaxies, where we can resolve the sphere of influence of the black hole, we can actually take the motion of stars and ionized gas at the centers of the galaxies, and we can use that motion to measure the mass of the black hole at the center. But for galaxies outside the nearby universe, where we can't resolve the sphere of influence of the black hole, we need to find an alternate method to do this. And the way that we do this is by looking at AGN, or active galactic nuclei. So here's a quick reminder of what's going on at the center of an AGN. We have a supermassive black hole at the very center that's surrounded by an accretion disk. There's some other stuff going on there. We have a corona of gas sort of toward the center. We have an accretion disk around the supermassive black hole. And farther out, we have what's known as the broadline region, where you have sort of clumpy-ish gas that's in virial motion around the supermassive black hole. And from there, we get broad emission lines. A little bit farther out, we have the narrow line region, which is a much more extended region. And there's some other features as well, such as these jets and the famous torus, which is an obscuring medium that causes a difference in what we observe depending on the angle that we're viewing the system. So if we're observing kind of up from the bottom here, then we see into the center of the system, and we actually get the broad lines and get to see the central source a lot better, the accretion disk. Whereas if we're looking in from the side here, then we see a lot more of the light is obscured. And so we don't see the broadline region or have a direct view of the accretion disk. So if you take a spectrum of an AGN or a quasar, so I'm going to sort of interchange AGN and quasar here throughout this talk. Historically, quasars are the more luminous versions of AGN, but essentially they're the same phenomena. So I'm actually probably going to be talking mostly about quasars during this talk because we're talking about much farther away, galaxies that are much farther away. So here is a composite image, a composite spectrum, excuse me, of what you might see in quasars in the UV and optical. So you can see there's lots of broad emission lines coming from the gas in the broadline region. And underneath the whole system, we have this continuum emission underlying the whole, across the whole spectrum. And we also have some other features such as narrow emission lines, and there's a lot of other species that sort of cause a lot of contamination to the emission lines. And for my purposes, it's contamination. I know for other purposes, this is actually very interesting. But for the purposes of today's talk, we're going to focus mostly on the broad emission lines in the continuum emission. So how do we use AGN to measure black hole masses? In order to do this, we need to know three basic quantities. The first is the velocity of the gas. Okay, we need to know how fast this gas is moving. We assume that the broadline region gas is in virial motion around the black hole, that its motion is dominated by the gravity of the black hole. So we need to know how far away that gas is from the supermassive black hole. And we need to know this factor F here accounts for the behavior or the distribution of the gas. So is the gas spherical in nature? Is it distributed in an accretion disk? What is the gas doing? Is it flowing out? Is it falling in? That sort of behavior is all subsumed under this factor F. And so if we can get these three quantities, then we can determine what the mass is in these quasars. So let's talk about each of these things. First, the velocity is pretty straightforward. The broad lines that we observe in quasar spectra are Doppler broadened. Okay, so if you have faster moving gas, you're going to have broader emission lines. And so essentially, if you can get a good measure of the line width of the broad emission lines, then that gives you the velocity of the gas. But things get a little bit more difficult once you start talking about how far away the gas is from the supermassive black hole, because the broadline region in all but the most nearby AGN is pretty much unresolvable. And it's on the order of micro arc seconds in angular extent on the sky. And so we can't just take an image and see how far away this gas is. We actually need to find some other way for us to measure how far away the broadline region is. And so the way that we do this is with reverberation mapping. So the idea behind reverberation mapping is that we have variability going on in both the continuum emission that we observe, which is shown here in this top little inset plot here, and the flux in the broad emission lines that we're observing, which I show here on the bottom. So this plot shows just the brightness as a function of time. And the continuum emission is coming from very close into the black hole. It's coming from the accretion disk, and the broad emission lines are coming from much farther out. And so if you observe the quasars over a long period of time, you can see that they vary, and the same signature of variability is seen in the continuum as in the broad emission lines. But there's a time delay between those two signals, and that time delay corresponds to the time it takes for the light to propagate out from the continuum region out to the broadline region here. So here's a little video that kind of demonstrates this. So you can see, some signal comes out from our supermassive black hole very close in. It travels out, and as our observer is sort of up here, we get a delayed signal from those outer regions, but we get an immediate signal from the continuum region. This particular video actually shows dust reverberation mapping from the dust torus, but it's the same principle. And so you can imagine the broadline region is somewhere in here as well. And the same idea goes. So you have this variability signal, some increase or decrease in flux that is later reverberates out to the broadline region. So if we can measure this time delay, that gives us the radius of the broadline region. So here's some actual reverberation mapping data. On the top panel here, I'm showing the flux in the continuum at 5100 angstroms. And in the bottom, we're showing the integrated flux in the H beta broad emission line. And so this is from a reverberation campaign that we carried out in 2010. The different colors are just other telescopes that also observed the same object. And so you can see there's a nice signature here in the top panel. You can sort of see the corresponding feature in the H beta line. And that time delay between the two signals is what we're looking for. And that time delay gives us the radius of the broadline region. Now, the broadline region is not all, it's not a thin ring necessarily, okay? And so what we're really measuring when we take the flux in the entire emission line is sort of a characteristic or emissivity weighted broadline region radius. So we're actually losing some information here when we just take the flux inside the whole broadline, but essentially that's what we need for black hole mass measurements. So for that purpose, it works just fine. So the last component of measuring the black hole masses is this factor F. And this depends on the geometry, the orientation, the angle of inclination, and what's going on in the broadline region. And this is similarly problematic because we can't resolve this region. And so here over on the right, I'm showing just a couple of models of geometric models of what the broadline region might look like. And until the past few years, really, we haven't been able to actually even produce these kinds of models. It's been relatively recently that this has been able to happen. And so generally what people do is actually measure an average F factor that is calculated by assuming that AGN must fall in the same M sigma relationship as quiescent galaxies. So this plot here in the gray points show quiescent galaxies that have black hole masses measured using stellar or gas dynamics nearby. So these are nearby galaxies that people have measured black hole masses for. And these blue points are reverberation mapped AGN before they've been measured or multiplied by this factor F. And so you can see here, this black line shows the M sigma relation. You can see that the AGN fall below this relationship. And so essentially what we do is we just determine what factor F do we need to multiply these masses by to put them on the same relation. And so that gives us an average F factor of the AGN sample, the reverberation mapped sample. And that is actually what is most frequently done when measuring supermassive black hole masses with reverberation mapping from here. But this isn't necessarily ideal. There's a few problems with this. One, we expect that each AGN should have a different F factor because there may be slightly different things going on in the broadline region, and we're probably observing them at different angles. So we actually don't expect the F factor to be the same. And the M sigma relationship might not be universal. There's been a lot of back and forth over the years about whether different types of galaxies follow different M sigma relationships. And there also may be an evolution in the M sigma relationship with redshift. So we might not be able to apply the same M sigma relationship to nearby AGN as we do high redshift AGN. And so this causes a lot of uncertainty in the black hole mass measurements. And the uncertainty in the F factor is actually the largest source of uncertainty we have in our measurements. And so this has been a problem for a while. But one thing that we can do to help work on this issue is use velocity resolved reverberation mapping techniques. So instead of measuring the flux in the entire H beta emission line, for example, if we actually measure the time delay between gas moving at different velocities as a function of, measure the time delay as a function of velocity of the gas, we then can actually get a little bit more information about what the broadline region is doing. So for example, here I show the different velocity bins that we've divided this H beta line up into. And you can see the time delay between the flux in each of these bins as a across the whole line. And you can see that the blue side of the line responds at much longer lags than the red side of the line. And this is actually a signature of infalling gas. So just by doing this crude division, just by binning up by velocity, we can actually get a little bit more information about what the broadline region is doing. And if we have very high quality reverberation mapping data, we can actually fit models to the light curves and the spectra simultaneously. And these models can give us both geometric models for the broadline region, and they can also give us individual F factor. We can back out the F factor for each of these individual objects pretty well. And so this gives us a much better sense for what the broadline region is doing than if we're just doing sort of the integrating the full emission lines. We don't get any detailed information from that. But it's only been, again, over the past 7 or 8 years, reverberation mapping has been going on for decades. And it's just over the past 7 or 8 years that we've really been starting to get good enough data, high enough quality reverberation mapping data that we can make these kinds of models. So in practice, reverberation mapping is extremely observationally intensive. You require high signal to noise spectra because you need to be able to disentangle different parts of the emission lines from any contaminating species and make sure that you're getting good measurements of the continuum. You need flux measurements that are accurate to within a few percent because we're relying entirely upon variability signals. And so you need to be certain that your variability that you're observing is not due to calibration issues or just uncertainties in your spectrophotometric fluxes. You need to have a good handle on that. You need long time campaigns. You need your campaigns to last ideally at least 3 times the time scale of interest, so that not only are you you have a good chance of seeing variability happen in the continuum, but you also need to be observing for long enough that you then see the response. And so for high luminosity and emission lines that are farther out, you sometimes have very long time lags. And so you need to have very long campaigns in order to actually make a measurement. And you also need a high time sampling relative to the expected lags that you're measuring. If you have a time delay of only 3 or 4 days, you're not going to be able to detect that if you're only observing the object once every 2 weeks or a month. So you need to have very high time sampling. And so one single reverberation mapping measurement is very observationally expensive. And so this plot that I'm showing here is 180 days of nightly observing for what we were able to observe 5 or 6 objects over the course of a night. So we were able to get measurements for 5 objects, but it took 180 days of straight observing, which took like 30 observers, and followed by 2 years or so of dedicated grad student my time. And so that got us 5 reverberation mapping measurements. And so over the course of the past few decades, doing these experiments with single slit spectrographs, we've managed to amass measurements for roughly 60 to 70 nearby AGN. And so the reason that we don't have a much bigger sample is just because it's very difficult, it's very observationally intensive work to do. But there's been a really useful thing that has come out of these 60 or 70 measurements that we've done using these single slit spectrographs. And that is the radius luminosity relationship. So this here shows the broadline region size, so essentially the time delay that we measure as a function of the AGN luminosity. And you can see there's a very nice correlation here. And the existence of this correlation allows us to make black hole mass measurements using a single spectrum. So if we have a very well calibrated relation, all we need is to measure the luminosity with a single spectrum. We can then extrapolate up to this relationship, determine what the broadline region size must be. And if we can make a decent line width measurement from that spectrum as well, then we can make a black hole mass estimate. And so this relationship, since it became known, has been used to make black hole mass estimates in samples of thousands and thousands of quasars across the observable universe. And so that allows us to sort of skip over the very heavy observational requirements of reverberation mapping. But I'm going to come back to this later on. So what I've talked about mostly so far have been what I sort of refer to as traditional reverberation mapping campaigns, where we have telescope time on sort of a modest sized telescope. We carry out observations over a single observing season. We're using a single slit spectrograph, which means that we can observe maybe a handful of AGN over the course of the season. These plots here are actually from an HST campaign that we carried out back in 2014. So these are UV light curves, but you can see that they're very high signal to noise light curves. We have very high signal to noise spectra. We get a lot of detail about these types of objects, but we are typically restricted to nearby low luminosity AGN when we do this, because we need objects that are going to have time delays that we can measure over a single season instead of needing multiple years and multiple seasons of observing. So the main goal of this type of reverberation mapping campaign is to obtain these velocity resolved reverberation mapping results, maybe potentially fit some models like we've started doing, measure properties of the accretion disks. We can do reverberation mapping with different continuum bands to learn about the accretion disk itself, and to just essentially learn as much as we possibly can about a small number of objects. But more recently, we've actually started to move on to more large-scale multi-object reverberation mapping experiments. And these are carried out on survey telescopes that are operating over several years instead of just single seasons. And we're using multi-object spectrographs, so we can observe hundreds of AGN at a time instead of just a single one. Now, the thing is that we typically, because we have a range of objects, we tend to get lower signal to noise data, but it's still doable. So the main goals of these types of campaigns are to measure the black hole mass in a much larger uniform sample of quasars. We want to push up to higher redshifts. We want to populate the high luminosity end of the radius luminosity relationship, where there hasn't been a lot done before. And we also want to look at other emission lines that people use to measure black hole masses. When we're looking at higher redshift objects, people start to use emission lines like magnesium-2 or carbon-4. And here on the bottom panel here, I'm showing the carbon-4 radius luminosity relationship. You can see it's not very well populated at all. And so one of the goals of these large multi-object reverberation mapping campaigns is to define radius luminosity relationships for these other emission lines, because people are already using these emission lines to estimate black hole masses using the single epoch methods. And so what we need to do is really make sure that this is being done properly, and that we can actually use these other emission lines. And because we're looking at a large uniform sample of quasars that spans a much broader range in redshifts, we can actually also use these types of campaigns to look for evolution in the relationships between black hole mass and various galaxy properties as well. So these are these types of campaigns have different goals than the previously discussed types of campaigns. So one project that I've been involved in now for several years is the SDSS reverberation mapping project, which is led by your very own Yue Shen. So Yue and I have been working together now for several years and collaborating very closely on these reverberation mapping projects. So the idea is, so some of this is probably something that you guys may have heard from him. But so the SDSS reverberation mapping project, or SDSS-RM, we were monitoring 850 quasars ranging at redshifts ranging from 0.1 all the way to 4.5 in a single field with the BOSS spectrograph. So instead of just a handful of objects, we actually got 850 each time. The spectra that we got from SDSS were also accompanied by photometric light curves. So we also observed these fields with a number of other telescopes, including the Steward Observatory Bach telescope, which is right behind me, actually up in here, that one right there. And we're also observing with the CFHT in Hawaii. And we have this field actually falls within the Pan-STARRS survey as well. And so we have dense photometric light curves running all the way back to 2010 for this particular field. And since we began monitoring with SDSS, we've also obtained a lot of follow-up with various other telescopes such as XMM, Spitzer, and HST. So there's been a lot of different types of data accrued on this particular field. And it's been highly successful. So we observed these sources starting in 2014. And so far we've published measurements using just the first 4 years of data. But with only the first 4 years of data on this single field, we've added about 150 black hole masses to the sample of black hole masses. So this plot here shows black hole mass as a function of redshift. All of the gray points were the decades and decades of single measurements that have been accrued over the years. And all of the colored points are masses that have been measured by the SDSS-RM program, so our work. And so you can see that there was a handful of higher redshift sources that were measured ahead of time. But in general, this is the first large sample of mass measurements at redshifts greater than 0.3. And we've filled in a huge amount of this parameter space in this plot. And so, we've taken the 60 or 70 measurements that had taken decades to acquire, and done with just the first 4 years of data, we took that up to now over 200 total measurements in the reverberation-mapping database. So,
Kate?
Yeah.
So is the lower envelope of that scatter plot determined by the cadence of the observations?
Let's see. Yeah, so that's definitely a selection effect. Some of it's the cadence, some of it is just luminosity constraints. We have luminosity, at higher redshifts, we can only observe the more luminous bunch. So we're looking at higher black hole masses. Yeah. So we do expect that there's objects down here. We just aren't able to look at them yet. But another interesting thing that has come out of this work has to do with the radius luminosity relationship. So the plot that I showed you before was, again, the broadline region radius as a function of luminosity. What the previous plot showed was essentially these blue points here. And you can see that the blue points fall very nicely on this measured relationship here. When you add in our measurements from SDSS-RM, things start to look a bit messier. And you can actually see that there's some green points too here that are also falling below the relationship as well. So there's a group, the Do-It-All papers, a group over in China who's been working on this as well. And they also have started finding outliers below the radius luminosity relationship. And when I first saw this plot, when I first drew this up for the paper, I was not happy. I was, oh no, what have I done wrong? Something has gone horribly wrong, because until now, this has been a very tight relationship. And so we were sort of expecting everything to fall very well on the radius luminosity relationship. And so after months of going through everything and making sure that nothing was goofed up, we decided that this was in fact what we were seeing. And there's been a couple of follow-up studies that have done simulations and tried to determine whether this is some sort of selection effect or what. But it turns out that this can't really be explained well, or it's not likely to be explained very well just by observational or selection effects. It turns out there's some physical reason why these sources are falling below the radius luminosity relationship. Now, this has actually pretty wide-reaching implications for black hole mass measurements, because pretty much anybody who's measuring a black hole mass in a high redshift quasar, typically using a single spectrum, is using some sort of equation that's calibrated from the radius luminosity relationship. So if it turns out that we can't apply this to all quasars, that's a problem for all measurements of black hole masses, pretty much beyond the local universe. Now, the reason we didn't see this before is because all of these blue points tend to be pretty local, low luminosity AGN that are chosen to be variable, that have pretty similar emission line and accretion properties in general. But the sample that we were looking at was a pretty much general, just random quasar sample that happened to fall in this field. And so it covers a much broader range of quasar properties than the AGN that are used to calibrate this relationship are. And so it turns out that when you start, and these green points from the other group are actually highly accreting AGN. And so it turns out that this radius luminosity relationship is not likely to just be universally applied across the entire universe. You need to know a little bit more about what you're observing. And so We actually think that the relationship is likely to depend on the UV optical slope of the spectral energy distribution of the AGN, which is affected by accretion properties. So over here on the bottom panel here, I show a couple of different quasar SEDs and that have different accretion properties. And you can see in sort of the UV optical range, this orange one in particular has a different accretion properties than these other ones. You can see there's a difference in the slope of the SED there. And so because what we're measuring here is the optical luminosity and not necessarily the ionizing luminosity, which is in the ultraviolet, this actually matters. And so what we think is that we may be able to correct for this, but it will require knowing a little bit more about the AGN that you're applying these relationships to. And so now actually we've started doing a lot of work on trying to figure out, exactly what the cause of this discrepancy is. We've been observing these sources with HST to try to get UV, a handle on what they're doing in the UV. And we are mining through other data that exist as well to try to figure out what exactly is going on here. So this is something that we're really hoping over the next few years we'll be able to say a lot more about and hopefully correct for, so that we can be sure that people are using the radius luminosity relationship properly when they're applying it to measure black hole masses. So we were also able to measure relationships for the carbon-4 and magnesium-2 emission lines, which are often used to make measurements in higher redshift sources. You can see that these look a little bit more of a mess. So the magnesium-2 relationship previously only had 3 measurements in it. So we now have around 50 or so. And you can see that it's a little bit, there's a lot of scatter there. Some of that could be from the same issue that we're seeing more scatter in the H-beta relationship. It could also have something to do with the emission properties of magnesium-2. It's a little bit different than H-beta. And carbon-4, we were able to fill in a previously unpopulated region of the radius luminosity relationship, but we sort of got in trouble with selection effects here because our campaign is still not long enough to detect time lags that are sort of up in this region here. And so our relationship looks flat if you just look at our new points here, for example. And that's because we sort of hit our upper limit for lags that we can detect. So we are continuing to put our years and years of data together, and we're hoping that we will be able to start making some more leeway up on this region as well. So there's still a lot of work to be done on both of these relationships before we can really use them to make mass estimates. So to date, just from these 7 years of monitoring that we have done with SDSS-RM, there's been 29 publications that have come out, and they cover a huge range of topics. I mean, you can imagine you have 850 quasars with around 100 spectra plus hundreds of epochs of photometry. These papers cover things from reverberation mapping to host galaxy properties to broad absorption line variability to just emission line variability. There's a whole range of quasar physics and variability studies that you can do with these kinds of data. And we're not even done yet. So most of these studies have just been done with the first 4 or 5 years of data that we have. And we now are up to 7 years in spectroscopy. So we're still working on putting together the sort of final light curves from the program, which formally ended in 2020, and reporting on some of the final reverberation mapping and potentially other topics as well once we have these long time baselines. But we've actually moved on. So last year began the Sloan 5 program, and with that, the Black Hole Mapper Reverberation Mapping Project. So this project, so I guess I should back up for just a second. The SDSS-RM project was carried out essentially with extra time that we were able to get from Sloan. So this wasn't a dedicated SDSS program. It was actually extra time that was proposed to use for reverberation mapping. And we were able to get so much out of it that they decided as a part of Sloan 5, they were going to give us a expanded, enhanced reverberation mapping project. And so now we have a dedicated reverberation mapping component to the Sloan 5 program. So we're observing 5 reverberation mapping fields, 3 of which are in the north and 2 are going to be observed from the south. And instead of just getting 90 epochs over the 7 years, which is what we have from SDSS-RM, we're going to be getting 175 epochs over 5 years. And with these data, we're hoping to measure masses for on the order of 1,000 quasars instead of a handful, a few hundred like we are planning for the first one. So we started observing with SDSS-5, which began in fall 2020. Things have been slowed down significantly due to the pandemic, but unfortunately, I don't have any fun things to show you from the first year of data yet. We're just probably another month or two before I would have something interesting to show. But we have our first 3 fields, we have the first year of data for them. And so we're going to be starting to process those and see if we can get some of the shorter time lags measured in some of the low luminosity sources that we can measure in just a year. So we're really excited about this particular project. UA is, again, one of the leads on this particular project. And so we are, we're moving, and there's going to be a lot more coming out from our group and from probably other groups as well with these data. So we're really excited about this one. So now I'm going to switch gears just a little bit because I showed you that we had 29 papers that came out from the SDSS-RM program. And there's a lot of other science that can be done other than reverberation mapping. And so another topic that I've been interested in is broad absorption line variability. So most of my work is spent looking at emission line variability, but broad absorption lines are absorption lines that have widths that are greater than 2,000 kilometers per second. And they're thought to be produced by outflows that are launched from the quasar accretion disk. And if these outflows are energetic enough, they can travel out into the host galaxy and potentially be some way of providing feedback to the host galaxy. And so we really want to know what these what these outflows are doing and what the conditions are like that are causing these broad absorption features that we see in quasar spectra. And on the order of 10 to 20% of quasars have these broad absorption lines. So, it's really important because they're so common. It's another important thing that will help us just understand what's going on in these quasars. So like emission lines, these broad absorption features are variable. They've been found to be variable on many different timescales. But in the past, before programs like SDSS-RM, most quasars only had 1 or 2 epochs of spectroscopic observations needed to make these kinds of, to do these kinds of studies. And so there's been a lot of great studies done looking at timescales of months or years using a couple of spectra. But the high cadence of the SDSS-RM observations sort of gave us a unique opportunity where we could start to look at short timescale variability in these broad absorption lines and also, look at what patterns of variability these, we have 90 epochs. So we're not just looking at a single instance, a single change for each quasar. We're sort of looking at the behavior over a long period of time of these broad absorption lines. And it turns out that there's around 90 objects in the SDSS-RM sample that have BALs or things that are close to being wide enough to be considered BALs. So we've started looking at those as well. So for example, we found one object here. This is in the SDSS-RM sample that has a broad absorption line right here. Actually, it has 3 broad absorption features here. These 2 are on top of the carbon-4 emission line. And if you look at the root mean square residual spectrum, you can see there's quite a bit of variability in the trough, in the BAL trough. And over here, we show the equivalent width as a function of time during the course of these observations. And so you can see that there's quite a bit of variability. And we actually see some fairly substantial variability on short timescales on the order of a day or so in the quasar rust frame. And this hadn't really ever been seen before, mainly because there were not any data sets that had enough objects in them that we could expect to see something like this. And so we kind of went through to kind of determine what the potential causes of variability could be. We considered something like bulk motion or cloud crossing. Something is moving across our line of sight. And we think this is unlikely to be the cause in this particular source because the whole BAL varied as a unit, and it's too wide of a trough for that to really work. If we were to see something moving across the line of sight that is causing this, we would expect that the different parts of the trough would vary at different times. And we actually think that the most likely scenario is that the ionization state of the gas has changed. So the gas is somehow seeing a different amount of incident ionizing light, excuse me. So the reason why we think this is probably the case is because we see, again, these monolithic changes across the entire trough. We see coordinated variability in some of the lower velocity troughs, and there are some complications because we were looking at the light curves of the photometric light curves of this object, and we don't see the correlation that we expected to see between the continuum flux and the equivalent width. But we do think that something related to ionization variability is most likely the culprit. And we can use, excuse me, we can use this scenario, this likely cause of variability, to kind of pull out some of the physical parameters of the broad absorption line. So we can use the time scale of variability. We can use the recombination time, use that, set that equivalent to the recombination time, which gives us the density of the gas. And we can take that in combination with luminosities and some other parameters. We do have to make some assumptions here to get an estimate of how far away this gas is from the accretion disk. And so this gives us a little bit of information about what's going on, how much energy is in this outflow, and whether it's energetic enough to provide feedback to the host. And in this particular case, we find that it's not energetic enough to really affect the host galaxy very much, assuming that ionization variability is the cause of the variability. So that was just a study that we did on a single interesting object that we found. And so we followed that up with a sample study of all the BALs that we had in the SDSS-RM sample, and all of them that had high enough signal to noise that we could feasibly do a study like this, which ended up being about 27 quasars. And we actually found that roughly half of the BALs in this sample varied on these short time scales. And so it turns out that short time scale variability in these broad absorption lines is actually not that rare. It's just that we haven't had the data to detect it before. And this is just another example. This is another object that we observed. We can see the equivalent width as a function of time. You can see it's kind of all over the place. The red points are just sequential points that are very significantly different over short time scales. And you can see here, these are just two epochs shown together. You can see how dramatically the BAL varied over a short time scale of just 4 days in the quasar rest frame. So it turns out that, BALs have been seen to vary on all the time scales that they've been observed over, but it turns out that they even vary on the very shortest time scales that we can observe them on. And so now the models that people are coming up with to describe the production and the evolution of BALs and how they might interact with their galaxies need to take this into consideration. So they all need to take into account the fact that these BALs are varying on these short time scales. So that's pretty much all I wanted to show you. I'll leave you guys with my summary here, but I just wanted to say that, with data like these that we're having from these programs, we can just do so much, and on a whole range of topics. And we're really excited to continue over the next decade or so to get more data. So thank you very much, and I will take questions.
Thank you. Thanks for a very nice talk. Okay, so Brian Fields tells me he has a few questions, but he'll ask them in a bit. Or do you want to ask now, Brian? See your hand.
Oh, well, I can just ask one. Hi, Kate. It's good to see you, and great to hear about all this beautiful work you've done. So you showed all these beautiful observations, and I was wondering what's the status on theory? So there's some sort of sketches, but have people tried to make simulations of these broadline regions and see what happens if you illuminate them?
Yes. So people have been working on that. There hasn't been a lot of work done in relation to our SDSS work. Most of the theoretical work that's been done on the broadline region has been more in relation to the HST campaign that we did. We're doing another HST campaign right now. And those, we end up with UV, optical, infrared, all the way across the spectrum. We end up with a huge range of data. And so there's been a number of theorists who are working on broadline region models. I don't think there's been anything, I'm trying to think of if there's been anything like super exciting to come out of it yet. They're still working, but we have found that at least in the HST campaign that we did in 2014, the broadline region doesn't always nicely echo the continuum like we thought it did, which is a problem for reverberation mapping. And so there's been a lot of work done to try to figure out what happened there and why that happened. They think it's some sort of obscuring medium that arrived sometime during the campaign. And so that sort of has been the dominant, I guess, avenue of exploration that has come out from that.
Cool, interesting. Okay, and could that possibly shed light on, can they model the ionization state and see if that, because that was a concern for some of the later stuff you were talking about?
Yeah. Oh, so you mean like, are you talking about the radius luminosity relationship and the
yeah
there? So I think that right now nobody thinks that this has to do very much with like our understanding, I guess, of how the broadline region responds. I think it's more an issue of our assumptions that the optical luminosity is a good proxy for the UV luminosity, which you make when you plot the radius luminosity relationship is calibrated using the optical luminosity. And so I don't think there's been, at least to my knowledge, a lot of work done to try to explain this from an ionization standpoint, just because we think it's really just a problem with our observations, I think. It's just that we made an assumption that we could, the UV, the ionizing luminosity is expected to come from the far UV. And since we're not actually observing that, we're assuming that the optical luminosity is a good proxy for that, but it's not. It might not be. And especially, it may not be it may depend on the accretion properties of the AGN. So yeah, I'm actually not aware of much theoretical work that has been attacking this yet, but.
Yep, okay, got it, cool, thanks.
So I have a question. So I was very interested in the scatter you were seeing away from the radius luminosity relation with your new sample, and I was wondering to what extent have you does your sample cover a wide range of Eddington ratios for the quasars?
So that's something that we're working on right now. The problem with measuring Eddington ratios is that the Eddington ratio depends on the black hole mass, which depends on our measurements. And so you get this self-correlation. So you can't just measure the Eddington ratio from the black hole masses and the luminosities that we have. Right. And so that's actually something that we're working on doing with measuring the spectral energy distributions and trying to model the SEDs so that we can get an independent measurement of the Eddington ratio or something like that. That doesn't rely on our reverberation mapping measurements. Mm-hmm. So we're working on it, but I don't have a good answer for you yet.
Okay. Yeah, because I'm kind of curious whether you should expect to see kind of bimodal behavior depending on the form of the feedback and the type of accretion that's going on.
Yeah, so there has been a couple of papers published that suggest and show that Eddington ratio is likely the major contributor to this, the different radius luminosity relationships. But I'm not willing to call it solved just yet because of this. Some of the papers have been ignoring the fact that these measurements rely on black hole masses, which you end up just correlating things against themselves. And
right.
Yeah.
Okay. Do we have any other questions? I'm not seeing any. Let's let's see, give it a once, give it twice, and 3 times. Okay, let's thank Kate again for a great talk, and I hope you do get a chance to come visit in person at some point in the future.
Yes, thank you. Thank you for having me.
Thank you.
Thank you, Kate. That was a great talk.
Thanks.
So Brian, did you want to stick around?
Yeah, I mean, if that's okay, if you have a couple of minutes, Kate, that was a great talk. I just had a couple of,
Sure.
They're all naive questions. But, anyway, just great to see you, and congratulations on all the great stuff you've done.
Oh, thank you.